Dieppe, France, August 19, 1942. Of nearly 5,000 Canadian soldiers attempting to storm German-defended beaches, 3,267 are killed, wounded, or captured in 9 hours, a 68% casualty rate. The mathematics are brutal and simple. Existing landing craft force soldiers to climb over 4-foot sides, drop into chest-deep water, and wade 50 to 100 yards under machine gun fire. Average exposure time, 3 to 5 minutes. U.S. War Department planners calculate that invading Europe by sea at these casualty rates means losing tens of thousands of men before noon on day one. Then a boat builder from New Orleans with sawdust in his pockets and zero patience for military bureaucracy tells admirals their entire amphibious doctrine is backward. His answer? Put a ramp on the front. The Navy's Bureau of Ships calls the design too simple and refuses to test it. By June 6, 1944, that simple ramp would deliver 156,000 Allied troops onto French beaches in 24 hours. How did one man's rejected idea become the boat that won the war? Hit subscribe to keep these buried chapters of history alive, the engineering, the courage, and the cold math that changed everything. And drop a comment letting me know where you're watching from. Always awesome to see how far these stories travel. Dieppe, France, August 19, 1942. Dawn breaks over the English Channel, and with it comes one of the most catastrophic military failures of the Second World War. Nearly 5,000 Canadian soldiers, supported by British commandos and a small contingent of American Rangers, attempt to storm 6 beaches along the French coast in what Allied planners call a large-scale raid designed to test German defenses and gather intelligence for a future invasion. The operation is codenamed Jubilee, and it will become a textbook example of how not to conduct an amphibious assault. The Germans, alerted by early reconnaissance and suspicious coastal activity, are waiting with machine guns, mortars, and artillery zeroed in on every meter of beach. As the first wave of landing craft assault vessels approaches the shore, soldiers realize with growing horror that the boats they trusted to deliver them safely into battle are fundamentally flawed. The LCA, the primary British landing craft, is a wooden box with steel armor plating and 4-foot sides that force troops to climb up and over the gunnels while the boat pitches in the surf. Men drop into water that ranges from waist-deep to over their heads, their boots filling instantly, their rifles held high to keep them dry. The distance from boat to dry sand varies from 50 to 100 yards depending on tide and luck, and every second of that journey is spent under direct fire from German positions overlooking the beach. Average time from disembarkation to cover, assuming the soldier survives, 3 to 5 minutes of complete exposure. The mathematics are brutal and unforgiving. On Dieppe's main beach, machine gun fire from pillboxes and fortified positions cuts down men as they struggle through the surf. Mortar rounds bracket the landing craft still approaching shore. Artillery shells explode among clusters of soldiers trying to advance across the exposed shingle. Tank support fails when Churchill tanks bog down in the loose rock and are systematically destroyed by German anti-tank guns. By mid-morning, the beach is littered with bodies, abandoned equipment, and burning vehicles. The Royal Regiment of Canada suffers 94% casualties in their battalion. The Essex Scottish lose 530 of 553 men. By the time British commanders order a withdrawal 9 hours after the initial landing, 367 Canadians have been killed, wounded, or captured out of approximately 5,000 who embarked. The casualty rate for Canadian forces is 68%. The raid accomplishes almost none of its objectives. The lessons, however, are written in blood and will reshape Allied amphibious doctrine for the remainder of the war. In Washington and London, military planners studied the Dieppe casualty reports with grim focus. The numbers tell a story that no amount of courage or tactical brilliance can overcome. If you force soldiers to climb out of boats into deep water and wade 50 yards under machine gun fire, most of them will die before they reach the beach. General George Marshall, U.S. Army Chief of Staff, reviews projections for Operation Overlord, the planned invasion of northern France. Current estimates call for landing 150,000 troops on the first day across 5 beaches, with follow-on waves bringing the total to over 1 million men in the first month. If casualty rates mirror Dieppe, the invasion will lose 100,000 men in the opening hours alone. The mathematics don't work. The logistics don't work. The entire strategic vision of defeating Nazi Germany by liberating Western Europe depends on solving a problem that has no apparent solution. How do you deliver tens of thousands of soldiers onto a hostile beach without losing half of them in the surf? The answer, improbably, already exists in a New Orleans boatyard built by a man the Navy has spent years trying to ignore. Andrew Jackson Higgins is 56 years old in 1942, a boat designer and builder with a temper as legendary as his skill with marine engineering. He stands 5 feet 8 inches tall, weighs 200 pounds, smokes cigars, drinks bourbon, and has made a career of building shallow draft boats for Louisiana oil companies, trappers, and rum runners during Prohibition. His specialty is craft that can operate in water so shallow other boats would run aground, navigating through cypress swamps and marshland where propellers would foul on vegetation and hulls would hang up on sandbars. The solution he pioneered in the 1930s is a tunnel stern design with a spokeless propeller recessed into the hull, allowing the boat to draw as little as 18 inches of water while running at speed. He calls it the Eureka boat, and it becomes standard equipment for anyone working in Louisiana's coastal wetlands. Higgins builds them by the dozens, each one custom-fitted to the client's needs, each one a testament to practical engineering over theoretical perfection. In 1938, Higgins reads a magazine article about Marine Corps experiments with landing craft in the Caribbean and writes directly to the commandant, offering to build something better than the Navy's standard designs. The Marines, desperate for equipment that actually works, invite him to submit a proposal. What Higgins shows them is revolutionary in its simplicity. Take the Eureka boat, widen the beam for stability, reinforce the hull with steel plating, install a more powerful engine, and add one feature that will change amphibious warfare forever: a steel ramp on the bow that drops flat onto the beach, allowing troops to walk straight out onto dry sand instead of climbing over the sides into deep water. The concept is inspired by photographs Marine Major Victor Krulak brings back from China in 1937, showing Japanese boats with ramp bows used during operations along the Yangtze River. Higgins sees the photographs and immediately understands the implications. If you can drive a boat directly onto a beach, drop a ramp, and have soldiers walk out in seconds instead of minutes, you reduce exposure time by 90%. You eliminate the climb over high sides. You eliminate the wade through deep water. You turn a death trap into a delivery system. The U.S. Navy's Bureau of Ships, the bureaucratic authority responsible for approving all naval vessels, rejects the design almost immediately. The official position is that the Higgins boat is too simple, too unconventional, and insufficiently tested for military use. The Bureau has already invested millions of dollars in the landing craft vehicle, a design with side doors and a more traditional hull form that aligns with Navy shipbuilding doctrine. The fact that the LCV doesn't work particularly well is less important than the fact that it was designed by Navy engineers following Navy specifications. Higgins, a civilian with no military experience and no political connections in Washington, is told politely but firmly that his services are not required. He responds by building the first prototype landing craft vehicle personnel at his own expense in May 1941, using his own money, his own materials, and his own workers. The boat is 36 feet long with an 11-foot beam, powered by a 225-horsepower diesel engine that can push it to 9 knots. It draws 3 feet of water when loaded with 36 men or a fully equipped Jeep. The bow ramp is operated by a simple hand crank mechanism and drops flat in 3 seconds. On paper, the LCVP can approach a beach at speed, hit the sand with enough momentum to hold position, drop the ramp, discharge its cargo in under 10 seconds, retract the ramp, reverse off the beach, and return to the transport ship for another load. The entire cycle from ship to shore and back takes 4 minutes. Higgins invites the Marine Corps to Lake Pontchartrain to watch it work. If the test fails, the program dies. If it succeeds, Higgins will have proven that the Navy's Bureau of Ships has been wrong for 3 years, and that thousands of lives could have been saved if someone had listened to the boat builder from New Orleans who understood that the simplest answer is usually the right one. Lake Pontchartrain, Louisiana. Summer 1941. The water is calm, the morning air thick with humidity, and a group of Marine Corps officers stands on a wooden dock watching Andrew Higgins prepare for the test that will determine whether his landing craft lives or dies in committee. The Marines have traveled from Quantico, Virginia with explicit instructions to evaluate the LCVP objectively and report back to Washington with their findings. They are skeptical. They have seen dozens of boat designs over the past decade, most of them promising revolutionary improvements over existing craft, and most of them failing under real-world conditions. The Navy's Bureau of Ships has already made clear that the Higgins boat is not their preferred solution, and the Marines know that endorsing a design the Navy opposes will create bureaucratic problems that could delay equipment procurement for years. But they also know that men are dying because existing landing craft don't work. And if this civilian boat builder from New Orleans has actually solved the problem, they need to know about it. Higgins himself pilots the first test run, standing at the helm with a cigar clenched between his teeth, throttle wide open, driving the LCVP at full speed directly toward a mud bank at the lake's edge. The boat's flat bottom and tunnel stern design allow it to skim across shallow water that would ground conventional craft. The spokeless propeller churning through silt and vegetation without fouling. At what seems like the last possible second before impact, Higgins cuts the throttle. The bow rides up onto the bank with a grinding scrape of steel on mud, and he yanks the hand crank that releases the ramp. The steel plate drops flat with a metallic clang, forming a bridge from the boat's interior directly onto solid ground. A squad of Marines charges out, boots hitting dry land, 8 seconds from ramp drop to full deployment. One officer times it with a stopwatch, another makes notes on a clipboard. A third walks the length of the boat, examining the hull for damage, testing the ramp mechanism, asking Higgins technical questions about load capacity and engine specifications. The test is repeated 6 times with different loads, different approach angles, different sea states simulated by having the boat run at speed through the lake's chop. Every time the result is the same. The LCVP beaches cleanly, the ramp drops in seconds, troops disembark faster than any landing craft the Marines have ever seen. By noon, the senior officer present radios Washington with a message that will change the course of amphibious warfare. This works. The Navy's Bureau of Ships does not share the Marines' enthusiasm. The Bureau has institutional reasons for preferring their own designs, political reasons for maintaining control over naval procurement, and financial reasons for continuing contracts with established shipbuilders who have government relationships dating back decades. Higgins Industries is a private company with no political leverage, no congressional allies, and a reputation for building boats for oil wildcatters and swamp trappers, not military vessels that will determine the outcome of global war. The Bureau schedules a series of comparison tests designed to evaluate the LCVP against the Navy's preferred landing craft vehicle, tests that Marine observers will later describe as rigged to favor the Navy design. The LCVP is loaded beyond its rated capacity while the LCV carries standard loads. The LCVP is tested in rough surf while the LCV is tested in calm water. The LCVP's engines are fueled with substandard diesel that causes performance problems, while the LCV receives premium fuel. Despite these obstacles, the Higgins boat consistently outperforms the Navy craft in every meaningful metric. It beaches in 2 feet of water versus the LCV's 4 feet or more. It unloads troops in 8 seconds versus 3 minutes for the side door design. It retracts from the beach without assistance while the LCV frequently requires towing. The Marines document every test, photograph every result, and compile reports that make the superiority of the Higgins design mathematically undeniable. The breakthrough comes not from Washington bureaucrats, but from a Marine Corps general who has spent his career thinking about amphibious assault and understands that equipment failures cost lives. Major General Holland McTeer Smith, known throughout the Corps as Howlin' Mad Smith for his legendary temper and his willingness to fight anyone who threatens Marine effectiveness, sees the LCVP in action during field exercises and immediately grasps its strategic importance. Smith is 59 years old in 1941, a veteran of the punitive expedition in Mexico in World War I, and the Marine Corps' senior expert on amphibious warfare doctrine. He has watched men die in training exercises because landing craft failed, has studied the British experience at Gallipoli where inadequate boats contributed to catastrophic casualties, and has spent years trying to convince the Navy that the Marine Corps needs purpose-built equipment designed for ship-to-shore assault rather than modified utility craft. The LCVP is exactly what Smith has been demanding, and he becomes its fiercest advocate, bypassing the Bureau of Ships entirely and taking his case directly to the Secretary of the Navy, to congressional committees, and to anyone in Washington with the authority to override bureaucratic resistance. Smith's campaign gains urgency after December 7, 1941. Pearl Harbor transforms theoretical debates about landing craft into immediate operational necessities. The United States is now at war in both Europe and the Pacific, and both theaters will require amphibious operations on a scale never before attempted. The Marine Corps needs thousands of landing craft, not dozens, and it needs them within months, not years. The Bureau of Ships, facing the reality that America must build an amphibious invasion fleet from nearly nothing, finally concedes that the Higgins design works and that further delays will undermine military preparedness. Contracts are issued in January 1942 for an initial order of several hundred LCVPs, with options for thousands more depending on production capacity. The price per boat is set at approximately $10,000, equivalent to roughly $175,000 in today's currency, a figure that reflects both the simplicity of the design and the urgency of wartime procurement. Higgins Industries, which employed fewer than 500 workers in 1940 building commercial boats, is now tasked with becoming a major defense contractor capable of producing military vessels at industrial scale. By mid-1942, Higgins has government contracts worth hundreds of millions of dollars, production targets that require building dozens of boats per week, and a problem that has nothing to do with engineering and everything to do with capacity. New Orleans has no steel mills, no established assembly line infrastructure for mass production, and a pre-war workforce of skilled boat builders that numbers in the hundreds, not the thousands, required for wartime output. The city's industrial base is oriented toward shipping, oil refining, and port operations, not shipbuilding. There are no templates for how to transform a regional boat manufacturer into a wartime production powerhouse capable of delivering vessels to both the European and Pacific theaters simultaneously. The solution will require not just industrial innovation but social transformation in a southern city where Jim Crow laws still govern daily life and where the idea of integrated workforces is considered not just controversial but illegal. Higgins will have to build not only boats but an entirely new model of industrial organization, one that challenges the racial and gender hierarchies of 1940s America while meeting production deadlines that allow no room for failure. The question is not whether the LCVP design works, that has been proven beyond doubt. The question is whether American industry can manufacture 20,000 of them in time to win the war, and whether a boat builder from New Orleans with no patience for bureaucracy and even less patience for segregation can build a factory that works as well as the boats it produces. Higgins Industries, New Orleans, January 1943. The shipyard runs 3 shifts, 24 hours a day, 7 days a week, the night sky lit by welding torches and the constant hammer of rivet guns driving steel plates into hull frames. The scale of the operation would have been unimaginable 2 years earlier, when Higgins employed 500 workers building commercial boats at a leisurely pace dictated by customer orders and seasonal demand. Now the workforce exceeds $25,000, the production floor spans multiple city blocks, and the assembly process operates with the precision of an automotive factory translated into the language of marine construction. At peak efficiency in mid-1943, Higgins Industries completes 700 landing craft vehicle personnel per month, an output rate that equals roughly one finished boat every hour of every day. Each LCVP requires approximately 8,000 pounds of steel, 225 horsepower of diesel engine, electrical systems, hydraulic ramp mechanisms, armor plating, navigation equipment, and hundreds of welds that must hold under saltwater corrosion and combat conditions. The transformation from raw materials to painted hull ready for delivery takes not weeks but hours, a compression of manufacturing time that represents one of the great industrial achievements of the American war effort. The pressure to maintain this output is relentless and unforgiving. Steel shortages plague the entire defense industry as shipyards compete for materials needed to build destroyers, aircraft carriers, submarines, and thousands of auxiliary vessels. Higgins receives priority allocations from the War Production Board, but the steel arrives in irregular shipments that force production managers to constantly adjust assembly schedules to match available materials. Engine manufacturers struggle to keep pace with demand, forcing Higgins to source diesel motors from multiple suppliers and modify mounting systems to accommodate different specifications. Quality control becomes a nightmare as the pace of production overwhelms inspection capacity. Early boats delivered in 1942 develop chronic problems. Hulls leak at weld seams, engines fail due to inadequate weatherproofing, ramps jam from saltwater corrosion of the hand crank mechanisms. The defect rate in the first year of mass production reaches 18%, meaning nearly one boat in 5 requires significant rework before it can be certified for combat use. Field reports from the North African campaign in late 1942 document mechanical failures that strand troops offshore, boats that take on water and sink before reaching the beach, ramps that fail to drop under fire. The War Department makes clear that these problems must be solved or production contracts will be shifted to other manufacturers who can deliver reliable equipment. Higgins responds with the same combination of engineering insight and industrial improvisation that characterized his original boat design. The factory floor is reorganized into 7 distinct assembly stations, each responsible for a specific component of the LCVP construction process. Station 1 fabricates the hull frame from pre-cut steel sections. Station 2 welds the frame and installs the tunnel stern propeller housing. Station 3 adds armor plating and deck. Reinforcement. Station 4 installs the engine, fuel tanks, and mechanical systems. Station 5 adds the bow ramp assembly, pre-welded off-site to ensure consistent quality and faster installation. Station 6 handles electrical systems, navigation lights, and radio equipment. Station 7 conducts water testing in a dedicated basin where each boat is launched, run through performance checks, and inspected for leaks before final acceptance. The modular approach reduces assembly time, isolates quality problems to specific stations where they can be addressed systematically, and allows for continuous training of new workers who can master one station before rotating to another. By 1944, the defect rate drops below 2%, a reliability standard that equals or exceeds any other military vessel produced during the war. The workforce that makes this possible represents a direct challenge to the social order of the segregated South. New Orleans in 1942 operates under Jim Crow laws that mandate separate facilities for white and black citizens, prohibit integrated workplaces, and enforce wage differentials that pay black workers substantially less than whites for identical labor. Higgins, who grew up in Nebraska and has no patience for Southern racial politics, announces that his factory will hire on the basis of ability and pay on the basis of work performed, with no segregation of work crews and no separate facilities. Black workers and white workers will assemble boats side by side, use the same tools, eat in the same cafeterias, and receive identical wages for identical jobs. The policy triggers immediate opposition from local segregationist organizations, threats of legal action from state officials, and warnings from New Orleans business leaders that Higgins is violating both law and custom. Higgins tells them to stay out of his yard and continues hiring. By mid-1943, black workers constitute a significant portion of the Higgins Industries workforce, employed not just in menial positions, but as welders, electricians, engine mechanics, and quality control inspectors. The integration is not perfect. Social segregation persists outside the factory gates, and racial tensions occasionally flare into conflicts that require management intervention, but inside the shipyard, the policy is clear. If you can build a boat, you have a job, and the color of your skin is irrelevant to your paycheck. Women enter the workforce in comparable numbers and with similar resistance from traditionalists who insist that shipbuilding is men's work, requiring physical strength and technical skills that women supposedly lack. Higgins hires women for welding positions, engine assembly, electrical systems installation, and quality control inspection. Some are promoted to supervisory roles, overseeing mixed-gender work crews and making decisions about production schedules and material allocations. The women who work at Higgins Industries in 1943 are doing so not out of patriotic symbolism, but economic necessity and personal ambition, earning wages that exceed anything available in traditional female employment sectors. They learn skills that will serve them long after the war, master technical crafts that break down assumptions about gendered labor, and prove through daily output that competence has nothing to do with sex. Photographs from the period show women in welding masks and coveralls, work boots and safety goggles, operating the same equipment as their male counterparts and producing welds that pass the same inspections. The human cost of this production pace is measured in injuries, exhaustion, and the constant pressure of knowing that every delayed boat potentially costs lives overseas. Workers pull double shifts when materials arrive late, sleep in factory dormitories when transportation becomes unreliable, work through holidays and weekends because the invasion schedule allows no breaks. The accident rate in shipyards nationwide is among the highest of any wartime industry, with welding burns, crushing injuries from steel plates, falls from scaffolding, and dozens of smaller injuries that go unreported because taking time off means falling behind quota. Higgins Industries is no exception. The medical office treats hundreds of injuries per month, some minor and some serious enough to end a worker's career. The pace never slows. By December 1943, Higgins has delivered 12,000 LCVPs to the U.S. military, boats that are already in service from the Solomon Islands to the Mediterranean, from Alaska to North Africa. The vessels have been tested in tropical heat and Arctic cold, in calm harbors and storm-tossed seas, and they have proven their worth in combat operations from Guadalcanal to Sicily. But they have never been tested in the operation for which they were specifically designed: a full-scale amphibious invasion of a heavily defended European coastline against an enemy expecting the attack and prepared to inflict maximum casualties. The target is Normandy. The date is June 6, 1944, and the only way to know whether 12,000 Higgins boats can deliver the largest seaborne invasion in human history is to load them with soldiers and send them toward the beaches of France. English Channel, April 1944. Exercise Tiger, a full-scale rehearsal for the Normandy invasion, unfolds in the cold waters off Slapton Sands on England's southern coast, a stretch of beach selected because its geography resembles the landing zones in France. The exercise involves 30,000 American troops, hundreds of landing craft, naval gunfire support, air cover, and every element of the amphibious assault doctrine that will be tested in combat within weeks. The operation is meant to identify problems, refine procedures, and build confidence among soldiers who will soon face German defenders along the Atlantic Wall. Instead, it becomes a catastrophe that exposes critical failures in communication, training, and basic operational security. In the early morning hours of April 28th, 9 German E-boats, fast attack craft operating out of Cherbourg, intercept a convoy of LSTs, the large landing ship tank vessels that carry smaller craft and vehicles across the channel. The German boats fire torpedoes into the convoy, sinking LST-507 and LST-531, damaging LST-289, and killing 749 American soldiers and sailors in minutes. The deaths result not just from enemy action, but from cascading failures that reveal how unprepared Allied forces are for the complexity of coordinated amphibious operations. Allied warships escorting the convoy are operating on different radio frequencies than the transport vessels, making communication impossible when the attack begins. Soldiers below decks have been instructed to wear life vests, but many have put them on incorrectly, cinching the vest around their waists instead of under their arms, causing the vests to ride up and force heads underwater when men jump into the sea. Others are trapped below decks when torpedoes rupture hulls and compartments flood faster than evacuation can occur. The cold water of the channel, hovering around 50 degrees Fahrenheit, kills men through hypothermia within minutes, even if they survive the initial sinking. The disaster triggers an investigation that uncovers problems extending far beyond the E-boat attack. Exercise Tiger has revealed that despite months of preparation, Allied forces are not ready for D-Day. Radio communication protocols are inconsistent across units, with Army, Navy, and Air Force elements using different frequencies, different code systems, and different terminology for the same operations. Coxswains piloting the LCVPs, the men who will guide boats through rough seas and enemy fire to deliver troops onto the beaches, average only 8 weeks of training, much of it conducted in calm waters that bear no resemblance to channel conditions. Many have never practiced a landing under live fire, never navigated at night using only compass and dead reckoning, never dealt with the mechanical failures that plague boats operating in salt water and heavy seas. The boats themselves, though proven in design, suffer from maintenance problems that multiply under operational stress. Cold North Atlantic water is harsher than the tropical climates where LCVP saw their first combat in the Pacific, and engines designed for warm weather operation develop starting problems in near-freezing temperatures. Fuel lines freeze, electrical systems short out from spray and condensation, hydraulic ramp mechanisms seize from salt corrosion. There is no time for major design modifications or equipment retrofits. The boats staged in England, over 2,500 LCVPs loaded on transport ships and waiting in harbors from Portsmouth to Plymouth, are the boats that will carry the invasion. They must be made ready as they are. The solution comes not through hardware changes, but through an intensive, compressed training program that focuses on the human element of amphibious warfare. The Navy institutes a crash course for coxswains that replaces classroom instruction with practical drills conducted under conditions that simulate combat as closely as peacetime training allows. Live fire exercises become mandatory, with troops and boat crews practicing landings while artillery shells explode in designated impact zones offshore, and machine gun fire passes overhead at safe but psychologically realistic distances. Night navigation drills run continuously through May, with coxswains learning to pilot LCVPs in complete darkness, using compass bearings and timing to find beaches they cannot see, coordinating with other boats through hand signals and shaded lights that won't attract enemy attention. Storm simulations force crews to handle boats in rough seas, teaching them how to manage 6-foot swells that can swamp an overloaded craft, how to approach a beach at an angle that prevents broaching, how to retract from the sand when waves and enemy fire make every second count. Radio communication protocols are completely overhauled, with standardized frequencies assigned across all services and simplified code words that reduce confusion during the chaos of assault. Troops are re-drilled on life vest procedures, shown explicitly how to wear the vest properly and what to do if they must abandon ship in cold water. Medical teams practice hypothermia treatment, preparing for mass casualty scenarios where hundreds of men may be pulled from the channel suffering from exposure. By June 1st, the training completion rate reaches 89%, meaning 9 of every 10 coxswains scheduled to pilot boats on D-Day have been certified through the accelerated program. The remaining 11% are either still in training, medically disqualified, or replaced by more experienced boat handlers transferred from other theaters. The mechanical readiness of the LCVP fleet improves through round-the-clock maintenance that addresses every identified problem, replaces worn parts, and adds cold weather modifications to engines and fuel systems. The 189 LCVPs, staged in English ports in early June, represent the operational boats available for the first wave of the invasion, a number that reflects both the massive production output of Higgins Industries and the reality that hundreds of other boats are unavailable due to mechanical problems, training exercises, or deployment to other theaters. The force is as ready as it will ever be, which is not the same as being perfectly ready, but is the best that human effort and limited time can achieve. The calculus of war allows no more delay. General Dwight Eisenhower, Supreme Commander of Allied Expeditionary Forces, reviews weather forecasts that show a narrow window of acceptable conditions for the assault, weighs the risks of postponement against the risks of attacking with imperfect preparation, and makes the decision that will determine whether the Higgins boat fulfills its promise or becomes another failed design buried under the casualties of an impossible mission. June 5, 1944. At Supreme Headquarters Allied Expeditionary Force, a converted manor house in Portsmouth, Eisenhower gives the order that sets Operation Overlord in motion. That night, under cover of darkness and in seas rougher than planners hoped but calmer than the storm that has just passed, transport ships carrying the invasion force move into position 12 miles off the Normandy coast. At 0200 hours on June 6th, the first LCVPs are lowered from davits on the sides of transports, each boat swaying as it descends on cables toward water that churns with 6-foot swells. Soldiers climb down cargo nets in full combat gear, rifles slung across backs, packs heavy with ammunition and supplies, stepping from rope to boat in darkness while the vessels rise and fall with the waves. Some men miss their footing and plunge into the channel. Some boats swamp immediately, taking on water faster than pumps can clear it, sinking before they can disengage from the transport. Others circle in the darkness, coxswains struggling to find their assigned positions in a sea crowded with hundreds of boats, each one trying to form up into waves that will hit the beaches in coordinated succession. The plan calls for precision. The reality is controlled chaos. But most boats find their heading, form into lines, and begin the 12-mile run toward beaches codenamed Utah, Omaha, Gold, Juno, and Sword. In New Orleans, 3,000 miles away, Andrew Higgins sits by a radio, listening to the first reports from Normandy, waiting to learn whether the boat he built in 1941 will deliver the largest invasion in history or sink beneath the weight of expectations no simple design should be asked to bear. Omaha Beach, Normandy. June 6, 1944, 06:30 hours. The first landing craft vehicle personnel of the initial assault wave drives through the surf at full throttle, its flat bottom riding up onto the sand with a grinding scrape of steel on stone, the bow lifting slightly as momentum carries the boat as far up the beach as physics and engine power allow. The coxswain yanks the hand crank mechanism and the steel ramp drops forward with a metallic clang, falling flat onto the sand exactly as Andrew Higgins promised it would 3 years earlier when Marine officers watched him test the design on Lake Pontchartrain. 36 men of Company A, 116th Infantry Regiment, 29th Division, surge out of the boat's interior, boots hitting French soil, rifles at the ready, running toward the seawall 200 yards distant across open beach. The time from ramp drop to full disembarkation is under 10 seconds. Behind this first boat, 1,089 LCVPs are making repeated runs between transport ships anchored 12 miles offshore and 5 landing beaches stretched across 50 miles of Norman coastline. Each boat carries 36 combat-loaded infantrymen or a jeep with crew or ammunition and supplies for the troops already ashore. The mathematics of the operation are staggering in their scale and precision. To land 156,000 Allied troops in the first 24 hours requires more than 4,000 individual boat runs, each one navigating through rough seas, avoiding underwater obstacles, timing the approach to minimize exposure to German artillery and machine gun fire, discharging cargo, retracting from the beach, and returning to the transport ships for another load. The cycle repeats continuously from dawn until nightfall, with boats operating in shifts that allow for refueling, minor repairs, and crew rotation. The reality at Omaha Beach is far more chaotic and deadly than the planning documents suggested. German defenses are stronger than intelligence estimates predicted, with artillery positions overlooking the beach from high bluffs, machine gun nests positioned to create interlocking fields of fire across the sand, and underwater obstacles studded with mines designed to rip open landing craft before they reach shore. The initial waves suffer catastrophic casualties as German gunners target boats in the surf and cut down soldiers as they wade through the shallows toward cover. Many LCVPs are hit by artillery fire while still approaching the beach, shells punching through thin steel hulls and killing men packed tightly in the boat's interior. Others strike underwater mines that blow the bow off the craft, sending it to the bottom in seconds. Coxswains attempting to retract from the beach find their propellers fouled on obstacles or damaged by enemy fire, stranding boats in the surf zone where they become stationary targets for German gunners who methodically destroy them. The scenes are apocalyptic. Bodies float in the surf. Burning vehicles litter the sand. Wounded men crawl toward the seawall, seeking any cover from the relentless machine gun fire. By mid-morning, senior officers aboard command ships offshore monitor reports from the beach and calculate that the assault at Omaha is failing, that casualties are approaching levels that will make it impossible to establish a viable foothold, that the entire invasion may hinge on whether the troops already ashore can break through German defenses or will be pinned on the beach until they are systematically annihilated. What saves Omaha Beach is not revised strategy or reinforcements or naval gunfire support, though all of these contribute. What saves Omaha is the relentless mechanical continuation of the Higgins boat cycle. Despite the casualties, despite the chaos, despite the very real possibility that the next wave will suffer the same fate as the first, the LCVPs keep coming. Coxswains who watched boats ahead of them explode in the surf still drive their craft toward the beach, drop their ramps, discharge their troops, and retract under fire. Boats damaged by shell fragments or small arms fire continue operating until they sink or the crew is killed. Replacement boats filled with follow-on waves of infantry arrive at intervals precisely timed by assault plans drafted months earlier in England, adding fresh troops to the battle regardless of the tactical situation on the beach. The Germans, firing from positions that seemed impregnable, cannot kill men faster than the Higgins boats can deliver them. The mathematics that worked in favor of the defenders during the initial assault gradually shift as cumulative numbers overwhelm defensive positions. By noon, 34,000 American troops have landed at Omaha Beach. By nightfall, the beach is secured, German positions overrun or bypassed, and engineers are clearing obstacles to allow vehicles and supplies to move inland. The price is approximately 2,400 American casualties at Omaha, the highest of any beach on D-Day, but still a fraction of the catastrophic losses suffered at Dieppe 2 years earlier when 68% of Canadian forces became casualties in 9 hours. Across all 5 landing beaches, the results validate every promise Higgins made about his design. At Utah Beach, 23,000 troops land with only 197 casualties, the lowest of any assault zone, aided by accurate naval gunfire and the rapid deployment enabled by LCVPs that deliver troops directly onto sand in seconds rather than forcing them to wade through deep water under fire. At Gold, Juno, and Sword Beaches, British and Canadian forces using a mix of Allied landing craft including hundreds of LCVPs establish footholds and push inland against German resistance that varies from light to intense depending on the sector. By the end of June 6, 156,000 Allied troops stand on French soil, supported by over 10,000 vehicles ranging from jeeps to tanks to artillery pieces. The overall Allied casualty rate for D-Day is approximately 6.6%, a figure that includes killed, wounded, and missing across all 5 beaches. Compared to the 68% casualty rate for Canadian forces at Dieppe, the improvement is dramatic and directly attributable to equipment that works, training that prepared crews for the realities of amphibious assault, and a boat design that reduces exposure time from minutes to seconds. The cost in boats is also significant. More than 80 LCVPs are destroyed on D-Day, 55 of them at Omaha Beach alone, sunk by artillery fire, mines, or collisions with underwater obstacles. The losses represent less than 8% of the boats committed to the operation, an acceptable attrition rate given the intensity of the combat. In the weeks following D-Day, Higgins boats continue their work with mechanical reliability that becomes routine. The same LCVPs that landed the initial assault waves on June 6 run supply missions for weeks afterward, ferrying ammunition, food, medical supplies, and replacement troops from ships offshore to beaches that transform into massive logistics hubs. The boats operate in all weather conditions through storms that would ground larger vessels, their shallow draft and flat-bottomed hulls proving as valuable for sustained operations as for the initial assault. General Dwight Eisenhower, writing in his post-war memoir Crusade in Europe, offers the most concise assessment of the Higgins boat's contribution. Andrew Higgins is the man who won the war for us. If Higgins had not designed and built those LCVPs, we never could have landed over an open beach. The whole strategy of the war would have been different. The statement is not hyperbole. Without the ability to land troops directly onto hostile shores, the Allies would have been forced to capture ports intact before establishing a foothold in France, a strategy the Germans anticipated and prepared for by fortifying port cities and rigging harbor facilities for demolition. The Higgins boat made port capture unnecessary, allowing Allied forces to land anywhere along the coast and build their own logistics infrastructure on open beaches. The strategic flexibility this provided changed not just the Normandy invasion, but every subsequent amphibious operation in both the European and Pacific theaters. By the end of World War II, Higgins Industries and its licensees have manufactured 23,358 LCVPs, boats that participate in every major amphibious assault from North Africa to Sicily, from Anzio to the Philippines, from Iwo Jima to Okinawa. The total number of troops delivered to combat via Higgins boats is estimated at over 1 million, a figure that represents one of every 16 American servicemen who served overseas during the war. The design becomes the template for modern amphibious assault craft. Its basic principles: flat bottom for shallow draft, bow ramp for rapid deployment, simple mechanical systems for reliability incorporated into every landing craft developed in the decades following the war. Yet Andrew Higgins receives no government honors, no medals, no official recognition beyond Eisenhower's memoir and scattered mentions in military histories. His company, which employed 25,000 workers at peak production in 1943, is liquidated by late 1945 as canceled government contracts and the collapse of wartime demand make continued operation financially impossible. Higgins dies in 1952 at age 65, his contributions to victory largely forgotten outside military circles, his boats scrapped or sold as surplus, rusting in harbors worldwide. The lesson his life teaches is cold, clear, and measurable. Wars are won not by the most complicated plans, but by the simplest tools delivered at scale. Higgins proved that courage looks like engineering, that innovation happens when someone looks at an impossible problem and refuses to accept that the current solution is good enough. History belongs to the people willing to build it, one boat at a time, one ramp at a time, 10 seconds at a time.